Welcome to video 12 in our series on tensor calculus. This time we're going to follow up our last video with examples of the Jacobian using each of our four sample coordinate systems. We'll start with affine coordinates. Let me move down a little bit to give us some room. And I have already written down the definition of our Jacobian. Now, here, of course, is the definition that we had in our last video, but when you have an object like this that is got two free indexes in it, that means there are going to be 9 different entries, or in this case 4 because it's two-dimensional. It's often easier to see it if you represent it as a matrix, and that's what is often done with the Jacobian. So here is a matrix of the 4 possible combinations where we're taking the partial of z1 prime with z1, z1 prime with z2, z2 prime with z1, and so on. These are the 4 ways you can do it, and we organize it in something like this so that the first row is the first 1 prime row, the second row is the 2 prime row, and then the columns are the non-primed coordinate indices. All right, so that means that if we're going to take z1 prime with respect to z1, we're going to be taking the partial of x with respect to u. So let's go through these one at a time. This first one is the partial of x with respect to u, and that's just going to be a, because we treat everything as a constant except u. So a is a constant, u doesn't appear here, so that doesn't participate in the partial. Okay, now the partial of x with respect to v. The first term doesn't matter, so it's the partial of this guy, treating everything as a constant except v. And this will be b cosine alpha. Then the second row here is going to be y, the partial of y with respect to u, which of course is 0 because u doesn't appear there. And then the partial with respect to v, so it's just b sine alpha. So this then is the Jacobian for the affine coordinates. So let's drop those in place. All right, very good. Now let's see, let me change the definition. So this time we're going to find the inverse, which means we're taking the unprimed coordinates with respect to the primed coordinates. So here we're going to do the same thing we did before, only it's taking the partial of u with respect to x, y, v with respect to x and y. So let's go through those. This first entry will be the partial of u with respect to x, which is just 1 over a. Then the partial of u with respect to y, which is this second coefficient here, cosine alpha over a sine alpha. Then the second row is the partial of v with respect to x, which is 0, and the partial of v with respect to y, which is 1 over b sine alpha. So this is the inverse Jacobian, and it would look like that. Okay, if you get the idea, it's just very straightforward application of the formulas that we presented above. Okay, let me clean this up a little bit, and the next thing we want to do is to show you a sample covariant transformation and use that to derive the covariant basis vectors in affine coordinates as a function or in terms of Cartesian coordinates. So I'll remind you of what the covariant transformation looks like. It's covariant because the I-index, the free index, is on the bottom in the Jacobian. So since we're still kind of new in the syntax, I did this to expand it out. Remember what all this means, that the I-index is a free index, which means we have multiple expressions. Since we're dealing in 2 dimensions, we have 2 expressions. All right, and then the I prime index is a dummy index, which means that we have 2 terms which we add together. It's a summation over 2 values of I prime. So these are the explicit formulas that will let us derive the basis vectors in our affine coordinate system as a function of Cartesian coordinates. Okay, so what do we have here? Well, what is Z1 prime? Well, Z1 prime is x hat. That's the covariant basis vector 1 in Cartesian coordinates. So Z2 is y hat. And so if we're looking for our Z1 basis vector, we then have to multiply x hat by J1 prime 1, which is this guy over here, this A factor. And then the second term, we have to add J2 prime 1, which is the 0 guy down here. Okay, now if we do the Z2, we're going to take J1 prime 2, which is B cosine alpha, times Z1 prime, which is x hat. Then we add J2 prime 2, which is this B sine alpha term right here, times y hat. And of course we don't have to write this down because it's 0. So let's see if we got that right. And it looks like this. And indeed, what you see over here is exactly what we derived on this side. All right, let me point out something here that's significant. You'll notice that for our Jacobian inverse, and for the basis vectors, everything in these objects is constant. Nowhere in any of these things is there any dependence upon the variables u and v. And that means that the Jacobian, the inverse, and the basis vectors are the same throughout the entire space. Now that's a feature that's only true in general for affine coordinates. You will not find that to be the case when we talk about curvilinear coordinates. Okay, well now that we know what the basis vectors are in terms of Cartesian coordinates, then we can now go up and update our picture a little bit, because our picture should now reflect the fact that we know what our basis vectors are, and there they are. You saw this in the last demonstration, but now we have explicit formulas in Cartesian coordinate terms for those 2 basis vectors, and that would look exactly like that on our picture. Moving on now to plane polar coordinates, we'll move down and get a little space going here. We should be able to pick up the pace a little bit because we spent so much time on affine coordinates. So if we're going to do the Jacobian, we need to take the partial derivative of x with respect to r, and that's simply going to be the cosine of theta. R is variable, cosine theta is treated as constant, so partial of x with respect to r is that. Now the partial of x with respect to theta will be, we'll hold r constant, and that'll be minus r sine theta. All right, now moving on to y, the partial of y with respect to r is going to be simply the sine of theta. And then the partial of y with respect to theta is going to be positive r cosine theta. So that should be the Jacobian, and indeed it is. Okay, now let's do the inverse. So first we're going to take the partial of r with respect to x. So let's do that down here a minute. We'll do, let's see, that would be 1/2 of 1 over x squared plus y squared under the radical times the partial of what's inside, which is 2x. So the half and the 2x will cancel out, leaving us with x divided by x squared plus y squared under the radical like that. Now if we want the partial of r with respect to y, it's going to start out the same way, but this time this is going to be a y. We'll take 1/2 times 1 over x squared plus y squared under the radical times 2y. So this time the result is going to be y over x squared plus y squared under the radical, just like that. Okay, now let's find the partial derivative of theta with respect to x. So it's going to be 1 over 1 plus y squared over x squared times the derivative of y over x, the partial derivative, so y is a constant, so we're taking the derivative of 1 over x, so it's going to be negative 1 over x squared like this. Okay, so now if we multiply x squared through the denominator like this, take this factor and distribute it back through these terms, then we're going to get this as a result. We're going to get negative y over x squared plus y squared. Okay, now if we do the partial with respect to y, then what do we get? Everything's the same up to this point, but now we're going to take the partial with respect to y over x. This time x is the constant and y is the variable, so the derivative of that is just 1 over x. So if we multiply the numerator and denominator of this thing by x, then it'll be positive. It'll turn out to be this. It's x over x squared plus y squared when this distributes back through it. Okay, that should be our Jacobian inverse right there. Let's see if that works out. And indeed, that's the correct answer. Okay, so far so good. Okay, to get the basis vectors, we're going to multiply each item in the first column by the z1 prime basis vectors individually. So z1 is going to be this first term times x hat, and the second term sine theta times y hat, like this. All right, z2 is going to be this term and then this term times y hat. So r cosine theta y hat. Let's see if that works out. Yes, indeed, that's exactly right. So we're just applying the formula that we wrote out in detail in the last example. So finally, we'll use those results and we'll move back up to the top and update our picture. Now that we have explicit results for our covariant basis vectors, we can put those on the screen to look like this. And that's going to be it for plane polar coordinates. Now, cylindrical polar coordinates. The major difference here is we're dealing with 3 dimensions. So that means we're going to need the partial of x with respect to rho, which is cosine phi. The partial of x with respect to phi, which is negative rho sine phi. And then the partial of x with respect to z, which is 0 because it doesn't depend on z. Now for y, the partial of y with respect to rho is sine phi. And the partial of y with respect to phi is rho cosine phi, and again the partial of y with respect to z is 0. And the partial of z with respect to rho is 0. Partial of z with respect to phi is 0. And the partial of z with respect to z is just 1. So here we have the Jacobian, and indeed it's exactly what you'd expect. Now, it shouldn't be a surprise at all because, you'll remember these four elements are just what it looked like for plane polar coordinates in reference to r and theta. So again, cylindrical polar coordinates is really plane polar coordinates with an extra dimension. So it should be a very reasonable result here. Now, rather than go through all of the rest of it, I'm going to just show you the end result here. This looks exactly like plane polar coordinates, and we have this little guy that represents the z dimension. Okay, then if we're going to come up with the basis vectors, we're going to take every item in this column, multiply by x hat, y hat, and z hat respectively, and it's going to look like this. So cosine phi times x hat, sine phi times y hat, 0 times z hat, so there's no term here. Then we go down this column and take this factor, this one, and this one, multiply by x hat, y hat, z hat, and finally the last one, multiply 0, 0, and the only term that lives is this z hat. So these are the results for cylindrical polar coordinates. Pretty straightforward. And as before, we will quickly update the picture to reflect those basis vectors, and we saw this in our demo last time. And finally, spherical polar coordinates. By now you know the drill, so we're going to take the partial of x with respect to r, which is going to be simply sine theta cosine phi. Then the partial of x with respect to theta, which is going to be r, cosine theta cosine phi, and the partial of x with respect to phi, which is going to be minus r sine theta sine phi. And we do it for y. The partial of y with respect to r is sine theta sine phi. With respect to theta is r cosine theta sine phi, and with respect to phi is positive r sine theta cosine phi. And with z, the partial with respect to r will just be cosine theta. Partial with respect to theta is negative r sine theta. And since it doesn't depend on z, the partial with respect to z is 0. So that should be our Jacobian for spherical polar coordinates. And indeed, that's what it looks like. All right, now to find the inverse, we'd take the partial of r with respect to x, y, and z, theta with respect to x, y, z, and so on. Now, it's very straightforward, but the details become very tedious, and I'm sure you don't want to waste video time watching me take partial differentiation of each of these things, so I'll just give you the results. It's pretty intense, but it'll be good practice for you to go back and prove that that's exactly what you'd expect. And finally, the basis vectors are going to look like this because we're simply taking each column and multiplying each item in that column by x hat, y hat, z hat, respectively. Everything in this column right here, and everything in this column right here. And that's just a covariant transformation between the basis vectors in Cartesian coordinates back to the basis vectors in spherical polar coordinates. And finally, we'll go back up as before and update our picture. And that's going to look like this, as you saw in the previous demo. All right, hopefully all of that gives you a much better understanding and appreciation for the Jacobian and the covariant transformation.